Okay, so welcome everyone to the last session of today. We have lots of amazing short talks. The format is 12 minutes roughly for the talk and a few minutes afterwards for questions. And getting us started is Nick Early, who will take us on adventures in configuration space. Nick.
Thanks so much. It's great to be here virtually. I'd like to thank the organizers for the opportunity to share this work. It's based on this archive preprint that was just posted last week or so. So far we've been seeing this interplay between physics and geometry, sort of organized by several principles, and the ones I'd like to highlight here are those due to Kachazo, He, and Yuan, and Arkani-Hamed by He and Yuan, which give you a sort of dictionary between the moduli space of points on the projective line. In other words, in physical terms, the scattering equations give you some sort of equations on the space, and the physical interpretation of that would be Feynman diagrams. So on the left-hand side, we have an n-particle scattering process. Illustrated is a decomposition according to the some factoring channel, where some subset of particles go on shell. On the other hand, as you may have heard from Dmitry last week, I believe, the CHY formalism connects that to a sort of integral over the configuration space of n points on CP1. And in this work, what I'm going to do is start on this right-hand side with the geometry, discuss a generalization of that found in joint work with Freddy Cachazo, Alfredo Guevara, Sebastian Mizera, then sort of complete the square to the left-hand side. So the question is, if we have these physical processes here that are captured via CHY and ABHY by moduli space of endpoints on P1, the projective line, we have this bubbling phenomena to capture factorization. What's going to be the physical role for that? What's the physical interpretation? Okay, so passing from the top right to the bottom right, we have, instead of n points on P1, we have n lines in P2 or n planes in P3 and so on. So in here, you can see they're in like generic position, generic convex position. And boundaries, so you can imagine these lines sort of move around very nicely. And the boundaries of the space are captured by when some of these triangles shrink to a point. So here you can see the line 3 moves down until this line 2, 3, 4 shrinks to a point. And then we're passed to a moduli, to a boundary of this configuration space. So you'd like to understand that this is kind of the analog of bubbling, and you'd like to understand what happens here on the physics side. And in this construction, which we found, it turns out that the geometry of particle scattering and the physics of particle scattering in a precise way, very precise way, lives on the boundary of this new objects. All right, so it's backwards compatible, contains cubic scalar, contains the bijoint scalar or trace phi cubed as a special case, and we have some novel factorization behavior. So that's what I'm going to talk about for the rest of today. So a review of the bijoint scalar amplitude. You've heard this probably several times already in this conference. N-particle scattering processes in this theory, if we fix a color order or a planar order, they're constructed with Feynman diagrams, which are in bijection with triangulations of an n-gon, and they're explicitly constructed using where each inverse propagator is dual to one of the chords of a triangulation, and then you have to sum over all triangulations of that. And these explicitly give you the different Feynman diagrams of the theory, one for each triangulation. Now, residues here residues of Mn, I'll denote the bijoint scalar on n particles by M sub n, are of the same, they're always into products of lower point amplitudes of the same type. Okay, Mn goes to Mn1 plus 1 times Mn sub 2 plus 1. All right, so that's a significant, that's a profound, actually a profound feature and requirement of scattering amplitudes. So trace phi cubed, or the bijoint scalar, is a toy model, but as we'll see in a minute, it does contain amplitudes for actual particles. So yeah, so that's sort of what we'll see. So let's introduce this notation which you've seen, x sub ij, where ij is a chord of a polygon. You build Feynman diagrams by taking the products of all the chords and so on. Now for factorization, you draw a chord and then take all of the refinements of this subdivision of the triangle of the polygon that then you fill them in separately, and then you get this nice factorization into a product here. Okay, now we're ready for the framework with the CGM framework. So inverse propagators here. So first of all, the notion of Mandel-Stem invariance, we no longer have Mandel-Stem invariance Sij. We have tensorial objects, Sijk, Sijkl, and the analog of chords in this theory are also x. They're of the form x sub ijk, x sub ijkl, where ijk are not cyclically consecutive. Okay, so if you look in this formula, you'll never see x1, 2, 3 or x2, 3, 4. Those vanish. Those vanishing is equivalent to momentum conservation. So the first new case in this construction is the 6-point k equals 3 object, here written here in the x basis, has 48 generalized Feynman diagrams, and bijection with some very, very rich mathematical object known as the positive tropical Grassmannian. Yeah, so let's zoom in on one of these inverse propagators. One of the propagators, x135, and ask what the residue would be. So up here before, right, residues are usually products of two lower point things. Well, here, the residue where x135 equals 0 is a product of three 4-point amplitudes. Just this product of three 4-point amplitudes. All right, so that's kind of an indication something interesting is going on. So we'll return to this in a couple times here. So next, I want to take you beyond phi cubed to using recent work of Arkani-Hamed, Cao, Dong, Figueredo, and He, where they find real pion amplitudes and real gluon amplitudes inside trace phi cubed by taking some sort of deformation and expand with delta and expanding around delta equals goes to infinity. The moral of today's talk is that there is an analog of this story for CGM, and we have an analog of the NLSM, the nonlinear sigma model, amplitudes for real pions in this story. And just like for trace phi cubed, the generalization, we also have this notion of backwards compatibility. So quick review, here's how the NLSM emerges. You take the 4 or 2 endpoint trace phi cubed amplitude, and you take a deformation of the x odd with a plus delta, the x even with a minus delta, and then you expand in delta, where delta is infinity, and a bunch of lower terms cancel. Like here, the first non-vanishing term is that of delta to the minus 2. You extract the coefficient, and what they were able to show is that this procedure exactly captures the Feynman diagram expansion of the NLSM. So I'll just give you the result here in the case of n equals 6. So I want you to remember this formula, sort of. We have six contributions to the contact term and three otherwise. These three guys are the three four particle guys. Now for CGM, we have to rewrite the deformation rule just a little bit. So this is the writing x odd odd, x even even is equivalent to saying xij goes to xij plus delta times the size of the intersection of ij with 135 minus 1. So x13 is sent to x13 plus delta times 2 minus 1. Okay, and then we deform. So for CGM, what do? Well, we send xijk plus delta times ijk, the intersection of ijk with 1, 4, 7, 10, 13, and so on, and subtract 1 from that size. And then assuming n is a multiple of 3 in this case, and then we take the delta goes to the infinity limit again and extract leading order term. Let's return to that residue of M36. Okay, so we have this product of 3 4-point amplitudes. Well, if you apply this deformation, then 2 of the factors become NLSM amplitudes, and 1 of them becomes a trace phi cubed amplitude. Right? So you see, you already see that the NLSM model, the NLSM is emerging from this generalization. There's a second way it emerges. Even more satisfyingly, we consider the following deformation. We assume that n is even, and then we take the intersection of ijk with 1, 3, 5, 7 up to n minus 1, subtract 1. And so it follows from the joint work with Freddie Gachaza, we showed that for trace phi cubed, some residues of this amplitude coincide, some residues of the CGM amplitude coincide with the trace phi cubed amplitude. We compute this same residue in after taking this deformation, and we find this new amplitude, this new rational function. And you can see that we have 2 copies of the 6-point NLSM. Here we have the contact term twice. Here we have the 3 non-trivial contributions as well from the Feynman diagrams. All right, so I hope you see that something very cool is going on. And I guess I finish right on time. Thank you very much.
Any questions for Nick?
Hi, Nick. Can you say, is there an analog of the Adler zero for this CGM nonlinear sigma model?
Yes. So far as I was able to compute, yes, there does appear to be, and it's yes. So in the case that when we take this pure deformation when n is a multiple of 3, thanks for the question. When n is a multiple of 3, and we take a deformation like this, then yeah, so far as I was able to check, and I conjecture, so in general, yes, it does vanish. Yes. So it's in the process of figuring out what it means.
Other questions? If not, let's thanks Nick for a really clear talk.